Hi there. This is our second lecture on Turing machines. Remember, we introduced Turing machines in the previous lecture, and these are devices with the same nature like DFA and PDA. They have finite controls and tapes which have a beginning but no end. The main difference that a Turing machine has is that, first of all, is basically about the head that connects the finite control to the tape. So the Turing machine head is a read-write head. It can read what's on the tape and it can write symbols on the tape. And more importantly, it can move to the right as always, but it can also go back to the left, right? And that makes Turing machines very powerful, as we saw in the last lecture. And we also introduced what are called multi-tape Turing machines. These are Turing machines that have more than one, but finitely many tapes, each with its own head. And the heads of a multi-tape Turing machine are also allowed to read and write on the respective tapes. They are allowed to move to the right, to the left, but they can also stay put, stay in place on certain transitions. So by the end of this lecture, you should be formally and informally describe a non-deterministic Turing machine. So we'll introduce non-deterministic Turing machines. To construct a deterministic Turing machine, which is equivalent to a given non-deterministic Turing machine. So just like the case of NFA, for every non-deterministic Turing machine, there's an equivalent deterministic Turing machine, which was not the case for PDA, for example. Then we're going to look at designing Turing machines that compute functions on the integers. Then we'll move to a special type of Turing machine called an enumerator. We'll describe it, should be able to describe it formally or informally. To construct a Turing machine recognizing the language generated by an enumerator, and construct an enumerator generating the language recognized by a Turing machine. So enumerators are kind of Turing machine-like devices whose job is to print things, to enumerate languages, basically. So let's talk about non-deterministic Turing machines. A non-deterministic Turing machine is quite similar to the ordinary deterministic Turing machine, but with a finite number of choices for the next move for each state symbol pair, right? So given a certain state that the machine is in and a certain symbol that the head is looking at on the tape, there is a finite number of choices for what to do, right? And by what to do, basically we mean which state to enter, which symbol to write on the tape, and in which direction the head is to move, to the left or to the right. That's basically what it is. So the transition function for a non-deterministic Turing machine is the only thing that distinguishes its formal definition from a deterministic one. And the only difference, as you can see, is that, as always, the transition function delta takes a state and a tape symbol as input. And what it gives us back this time, now this P, remember, is the power set. So the range is the power set of this set. So what it gives us back is a set of triples, right? And each triple represents a choice for what to do. The next state, what to write on the tape, and the direction in which the head will move, whether to the left or to the right. Now, it should be clear that every deterministic Turing machine is a non-deterministic Turing machine in disguise. It just doesn't use its non-deterministic feature. It just never makes a guess. Basically, the sets that delta return are always singletons. They always contain a single triple. So let's start with an example. We would like to design a Turing machine which will recognize this language. Now, what is this language? Strings of zeros of the form 0 to the n, where n is not a prime number. Now, to be not a prime number, this means that n is the product of two integers other than 1 and n, right? So a prime number is an integer whose only factors are itself and 1. Now, being not a prime, being composite, means that you have other factors than yourself and 1, all right? So for example, 6 is not a prime because it's equal to 2 times 3. 7, on the other hand, is a prime because its only factors are 7 and 1. So what we have here is a string of zeros, and we would like to accept it if its length is not a prime number, all right? Now, if we're gonna think about this problem from the point of view of a deterministic Turing machine, then what you will basically need to do is to try to check all possible pairs of integers, whether they are factors of n, right? So one idea is to systematically start enumerating the integers, all right, or the pairs of integers from 2 to n minus 1, for example. And then you go ahead, okay, are 2 and 2 factors of n? Basically, is n the product of 2 and 2? Is n 4? Basically, is n the product of 2 and 2? Is n 4? Now, if this is not the case, then you try 2 and 3. If it doesn't work, you try 2 and 5. And so on through 2 and n minus 1. If that does not work, start with 3 and 3, then 3 and 4, then 3 and 5, then 3 and 6, through 3 and n minus 1. Then 4 and 4, 4 and 5, 4 and 6, and so on, until you reach n minus 1 and n minus 1. Now, of course, you can make this a bit simpler because there is a theorem that says that if a number is not a prime, then it has a factor that does not exceed its own square root. All right, so you don't need to go all the way up to n minus 1. You can just go all the way up to root n. But the problem is, to compute root n with a Turing machine, that's not very simple. All right. But there are ways to actually incorporate that. But we don't care about efficiency at this point. So basically, that's what you will need to do if you're using a deterministic Turing machine. But now, if you have a non-deterministic Turing machine, what can you do? How can that simplify the design? Now, let me remind you of non-deterministic automata in general. The power that non-deterministic automata have is just power to, or mainly it is the power to be able to describe computations in a simpler way, right? And the idea is that they can guess. And it's okay if they guess wrong, right? Provided that the only way they guess wrong is to reject a string that would be otherwise accepted if they guess right. Now, they should never make a guess that will allow them to accept a wrong string, a bad string, a string not in the language, all right? So for this language, for example, if you have a non-deterministic Turing machine and you give it a string of 7 zeros, now it needs to basically reject it, right? Because n is not a prime. So it should never make a guess that will allow it to accept that string. But if you give it a string of 6 zeros, now this is a string in the language. Now it can make a guess that will make it reject that string, provided that there is a way for it to make a guess that will accept it, all right? So that's basically just a reminder of what non-determinism actually is used for. So what would you do, right, if you have this power of guessing? What's a good guessing strategy for this language? Now, if you remember what we just said about how a deterministic Turing machine will treat this language, we said that it will basically search. It will try all possible pairs from 2 through n minus 1 and check if their product is n, right? If it is, then accept. If it's not for all of them, then reject, because this means that the number is prime, okay? So here's what you do. Instead of trying them all, just guess a single pair of integers between 2 and n minus 1, just one, and check if their product is equal to n. If it is, then n is not a prime. If it's not, you reject. Of course, by rejecting, you're really not sure that n is a prime, but the guess that you made and you commit to didn't work, right? But there is another guess, right? Given this guessing strategy, next time you run the same machine, it may guess the right pair, which are indeed factors of n, okay? So that's the strategy. The non-deterministic machine will guess a pair of integers between 2 and n minus 1, then will check if the product is equal to n. If it is, it accepts. If it's not, it rejects. Okay, you may ask, how will the Turing machine check if the product of these two integers is n? Now, we just did that in the previous lecture. Remember, we had the 3-tape Turing machine, right? Remember the language a to the I, b to the j, c to the k, such that I is equal to k. And we recognize this language with both a single-tape Turing machine and a multi-tape Turing machine, in particular a 3-tape Turing machine. And the idea is to put the first number, basically the IAs on one tape, then the JBs on the second, and the KCs on the third, and then we had to check if the product of I and J is k. Now that's exactly the same. You'll keep 0 to the n on the third tape. Then the first number, how are you going to represent it? Now the first number, which is between 2 and n minus 1, suppose you guessed 3, for example, you're going to represent it by 3 zeros. And the second number, suppose you 7, you're going to represent it by 7 zeros. Then basically you write 3 zeros on the first tape, 7 on the second, n zeros on the third, and then you check that the number on the third tape is the product of the two numbers on the first and second tape, exactly as we did with that example in the previous lecture. All right? Okay, theorem. Every non-deterministic Turing machine has an equivalent deterministic Turing machine. Right? So that's usually a very important theorem when we have the two things are equivalent. And here this basically says that non-determinism doesn't really give us any extra recognition power, right? It's just a way to allow us to describe computations more efficiently. All right? Now, this is exactly the case for finite automata, for NFA and DFA. For every NFA, there's an equivalent DFA. But it's not the case for PDA. So in the case of PDA, non-determinism does buy us more power, right? It allows us to recognize languages that we wouldn't otherwise be able to recognize. So how are we going to do this? Look, here's the proof idea. Suppose that n is a non-deterministic Turing machine running on some input w. Now, a deterministic Turing machine M, which is equivalent to n, should accept w if and only if there is a computation of n on w that halts in an accepting configuration. That's basically what it is. What do you mean by a computation of n? Meaning a sequence of transitions. All right, remember, because n is non-deterministic, it has several sequences of transitions on the same input string, right? Because with every transition, it has several choices to make. So, again, a deterministic machine M equivalent to n will accept w if and only if, exactly when there is a computation, at least one computation of n on w, that will halt, will actually stop, will reach a halting configuration, and that halting configuration is an accepting configuration. Now, M will actually need to keep track of all of n's possible computations on w, and it will need to do that by simulating them in parallel. All right? Now, if one of these computations halts in an accepting configuration, then M should accept. Okay, now before looking at how to do that, let's focus on this third point here. Now, what we said here is that M will basically try to keep track or simulate all of n's possible computations on w, right? But it will do that in parallel. Now, the question is, why in parallel? Why not sequentially? Why not simulate the first computation of n on w, and when it's done, go ahead and simulate the second computation of n on w, and when it's done, go ahead to the third, and so on. Why do we have to do them in parallel? Now, the same question actually was raised when we were discussing how a DFA will simulate an NFA. And in that case, we actually had the DFA simulate all the NFA computations in parallel, using this idea of having the states of the DFA being sets of states of the NFA. And what was the reason for doing it in parallel then? Now, the reason is the following. In the case of a DFA, right, and an NFA, the head can only move to the right. So if the DFA will simulate one of the computations of the NFA, with every step in that simulation, it will move the head one step to the right, and then when it reaches the end of the input, it will check if the NFA is in an accept state or not. It will accept if it is. If it's not, it needs to check the next computation. But the problem is that now the head has moved all the way to the end of the input, and it cannot go back. So for this reason, we were forced to actually do all the simulations in parallel. But this is not a problem for Turing machines. Turing machines can move their head back, right? And they can actually have multiple tapes. So if you're worried about the deterministic machine M changing the input as it is simulating n, you can keep a copy of the original input on a second tape, and whenever you're done with that computation of n, copy it back on the first tape and reset the head to the beginning and start all over again. So why don't we do that? Why don't we do the simulations sequentially? Why do we have to do them in parallel? Now, to answer this question, remember that on a given input, a Turing machine, like n, for example, right, may do one of three things. May accept the string, may reject it by entering the one and only reject state and halting, or may run forever on it. So this is the problem. This third possibility is indeed the problem. Because imagine that one of those computations of n run forever on w, right? Suppose that the first computation that m will simulate is a computation that runs forever on w, and the next computation accepts w, okay? Now, if we're gonna do the simulation sequentially, then m will start simulating the first computation on w, but that computation never halts. It never stops. So it will be stuck in that simulation forever, and it will never pay attention to the next simulation, which will actually allow it to accept the string. And if m will run forever simulating n on w, then it will run forever on w, and therefore it will not accept it, and thus it will not have the right behavior, because we want m to accept if n has an accepting computation, and n does have, but m is just busy simulating that infinite computation, which is totally irrelevant here. So for this reason, we're gonna do the simulations in parallel, so that we never get stuck with one computation that will take forever. Okay? Now, to see how we're gonna do this, let's look at what is called the tree of configurations. So this is a tree. Remember trees when we talked about them in our, I guess, third lecture or something? There were special types of graphs, and it's basically an undirected graph, all right, which has no cycles, except, right, it has no it has no simple cycles, right, if you remember what that means. And this is a rooted tree. There is a root here. So here's the idea. Suppose that this is the initial configuration of n on w, and that's unique. There is always a single initial configuration. Now remember what this means. So it means that n is in state q0, and the head is at the pointing at that a, and that's the string on the tape. So that's the input, for example, a, b, b, a. Because n is non-deterministic, it may have several next configurations. So this configuration, for example, corresponds to doing what? Changing the state from q0 to q1, writing a b over that a, right? So replacing the a with a b, and moving the head to the left. But because the head is already at the very beginning, at the leftmost cell, moving to the left will keep it in place. So the head is still pointing here, the state is now q1, and the symbol is b. What else can it do? It can do this. And what does that mean? It will change the state from q0 to q2, will replace that a with a b, and will move the head one step to the right. So now the head is pointing at this second b over here, this one. What does this mean? It's exactly the same, but replace the a with a c, all right, and also enters q2 and moves the head to the right. Now, what does that mean? So this configuration has a single next configuration, and in it the b will be changed to an a, the head will move to the right, and the state will become q3. What about here? So there are two possibilities for the next configuration. On this one, this b will be changed to an a, the head will move to the right, and q2 will change to q0. The state will become q0. What happened here? What happened is that this b was changed to an a, and the head moved to the left, and the Turing machine entered state q3. For this configuration, for example, what happened is that this b changed to an a, the head moved to the right, and the Turing machine entered q reject. Now remember, once a Turing machine enters its reject state, it halts. So there are no next configurations here, right? Now this one has an X configuration, right? Corresponding to moving to the right again, changing the B to the C. For this one, there is this configuration in which the B here was changed to a C, and the head moved to the right and the state became Q2. Or the B is changed to an A, the head moves to the right, and we enter Q accept. Now again, once the Turing machine N enters Q accept, it halts, so there will be no next configurations here. There could be next configurations here and here, right? Now let's look at that one. What is this? What did it do? Well, it replaced the B with a B, so nothing changed. It moved the head to the left, so it stays in place because it's already in the leftmost cell, and the state remains Q3. And there's a single next configuration here, which is this one. But now, because that's the same configuration, then its only next configuration is itself. And because that's the same configuration, then its only next configuration is itself. So it will keep on generating those configurations forever. So this is an infinite branch in the tree down here. This is a single computation, right? If you trace a path from the root, right? So this, then this, this, then that, and so on. This is one of the computations of n, and it's an infinite computation. This computation of n never halts. It runs forever. This over here is a rejecting configuration. It's a configuration that ends in rejecting the string. But this one over here is an accepting configuration because it ends up in an accepting computation because its last configuration is an accepting configuration. So what we need to do now is to have M basically construct this tree, right? Start with the initial configuration of n, then generate next configurations, and so on until it finds an accepting configuration, which means that there is an accepting computation here. But here is the thing. When we are doing this, right, we are basically searching for something. We are searching in this tree. Imagine that the tree is full in front of you. You are searching for an accepting configuration. All right? Now, there are several ways to search a tree. Now, two most important ways are called depth first search and breadth first search. When you do a depth first search, you go down a branch all the way to the end. So for example, if we're going to do a depth first search of this tree, we're going to start here, go to this, then go down, deeper, and so on until this branch ends. Then we will go here. If this doesn't work, we'll backtrack, go all the way up, start going this way, this way, this way, and all the way down. Once we're done, we go back to the kind of the deepest point that had a branching point. Then we try this branch. Now, of course, if you do that, you will find what you're looking for. But the danger in doing a depth first search is that if you start going down this branch all the way down until you stop, you will never stop. All right? Because of infinite branches, we should avoid depth first search. So we should do the other thing, which is breadth first search. And a breadth first search will basically generate the nodes in the tree level by level. So this is level 0, this is level 1, right, with these 3 nodes. This is level 2 with these 4, this is level 3, and so on. And the nice thing is that on each level there are finitely many nodes, because for every configuration there are finitely many choices for the next configuration. So there will always be finitely many nodes on each level. So you can't finish looking at all of them without running forever. And once and if there is an accepting configuration, then it must appear at some finite level in this tree, and you will eventually get to it. Now, if all the branches in the tree are either end in rejecting configurations or are infinite, then you will either reject by looking for all, if you do by doing a breadth first search, if there are no infinite branches and all the branches end with a rejecting configuration, this search will always hit a dead end. You will go level by level until you reach a level at which there are no nodes, right? You will not be able to generate more levels, and you never found an accepting configuration. In that case, you reject. But if there is an infinite branch like this one, right, and all the other branches end up in rejecting configurations, then basically the search will go on forever because the tree has infinitely many levels. And in that case, the DFA will run forever on the string, but that's okay because it's not accepted and n does not accept it either. All right? So here's what we said. So n's computation could be represented by tree. The nodes of the tree are configurations of n. The root is n's start configuration. Different branches correspond to different choices for the next configuration. A leaf of the tree is a halting configuration, and there could be an infinite path if one of n's computations does not halt. M will reach the tree, will search the tree for an accepting configuration. That's what we're looking for. To avoid searching an infinite path and taking forever down that path, depth first search must be avoided. So we're going to use breadth first search, meaning searching the tree level by simulating one step on each path. So here's how this will work. This is the tree just for reference here. So M will have two tapes. So before we start, we're going to do a pre-processing step. We're going to write the start configuration delimited by 2 hashes on tape 2. Now this is the start configuration. Q0, the initial state, followed by the input. So you will write, in this example for instance, we will write this configuration delimited by 2 hashes on tape 2. Okay, now here's the main loop. Replace the contents of tape 1 by those of tape 2. Now initially we have nothing on tape 1, so we will just copy the configuration here delimited by the 2 hashes onto tape 1. Then clear tape 2. Erase everything on tape 2. Now for each configuration on tape 1 delimited by 2 hashes, now initially here we only have one configuration, this one. Write all next non-rejecting configurations on tape 2, each delimited by 2 hashes. So because we only have one configuration on tape 1 here, which is this one, we're going to write all the possible next configurations, these 3, on tape 2 separated by the hashes. And we're going to write only the non-rejecting configurations. Now none of these is a rejecting configuration, so the 3 will be written on tape 2. Then we go back to step 1. Okay, what do? Replace the contents of tape 1, which is this guy, by those of tape 2. So we're going to copy those onto tape 1. Then clear tape 2. Now for each one of those, right, they are separated by hashes on tape 1 now, we're going to generate all possible non-rejecting next configurations on tape 2. So we're going to put this one, then these 2. Now, are we going to write this one on tape 2? No, because this is a rejecting configuration. You don't need to do it, right? You stop. You don't put it. So only these 3 will now be on tape 1. Okay. Now, when do we stop this loop? The loop ends if at step 3, when you're generating the next configurations, an accepting configuration is generated, or you don't find any new configurations to generate. There are no next configurations, all right? So if you apply this, if you go again back to step 1 on this example, now we had those on tape 2, all right? So, excuse me, they were on tape 1. So we're gonna replace what's on, we had them on tape 2, I'm sorry. We're gonna put those on tape 1 now, and we're gonna just clear tape 2. Then for each of those which are now on tape 1, right, after doing this copying, we're gonna generate all the possible next non-rejecting configuration and write them on tape 2. So this will be written on tape 2. Hash this, because it's the next configuration for this one. Hash this one, but that's an accepting configuration. Then we can stop and exit. All right? Good. Now, the second point that we want to talk about is using Turing machines as computers of integer functions. Look, so far, all the automata that we looked at, DFA, PDA, Turing machines, their only job is to recognize languages. You give them a string and they say yes or no, they accept or reject. Of course, Turing machines can run forever, but basically that's what you want them to do, right? To tell you something about a string, whether to accept or not. However, a Turing machine, because it can write on the tape, we can use it to do more interesting stuff, right? So you can think of Turing machines that we looked at so far that recognize languages or decide languages. You can think of them as Boolean methods, Boolean functions. You give them an input and they return a Boolean, true or false, yes or no, accept or reject. But we may use Turing machines to do more interesting computations, do arithmetic, for example. You give them an input, which is a number, and they do some computation on that number and they give you an answer. Now, how are we going to do that? Look, a Turing machine may be viewed as computing a function from the non-negative integers to the non-negative integers. So consider Turing machines whose input alphabet is the binary alphabet. So the input alphabet from now on will be fixed, just 0 and 1. Now, the non-negative integers can be represented, we can represent the non-negative integers in the decimal system, right? Decimal system of symbols. Now, the decimal system is based on an alphabet with 10 symbols. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? These are the 10 symbols of the decimal alphabet. And we can use those symbols to write strings that encode non-negative integers, as usual, right? We know how to do that, of course. But you also know about the binary system, which only has 2 symbols, 0 and 1, and you also know that we can encode non-negative integers using that alphabet by writing binary strings, each one of them corresponding to a non-negative integer. But you can also use what is called the unary system, and the unary system is based on an alphabet with a single symbol, just 0. And how are we going to use this alphabet to represent the non-negative integers? It's very simple. If you have a non-negative integer I, then it's going to be represented by I zeros. So now the length of the string of zeros represents the non-negative integer. So if you have 7 zeros, then that's a representation of 7. If you have 100 zeros, that's a representation of 100. If you have the empty string, which is 0, I0 that is, then this is a representation of the non-negative integer 0. Okay, so the empty string encodes 0. Fair enough? Good. So we're gonna encode the non-negative integers in unary. If a function on the non-negative integers takes k arguments, I1 through ik, takes k integers as inputs, then these arguments are initially placed on the tape of the Turing machine separated by 1s. So the 1 in the input alphabet just plays the role of the comma, right? But the integers themselves are represented by strings of zeros, okay? So for example, if you have a function that will take 2 and 3 as inputs, then you're gonna encode that input by having 0, 0, 1, 0, 0, 0. Now the 0, 0 at the beginning is an unary encoding of the number 2, then the 1 is the comma, the separator, then the 0, 0, 0 is the unary encoding of the number 3. If the machine halts, and we don't care whether it halts in Q accept or not, because we're not using it to tell us yes or no now. We're using it to compute something, to give us a result. If it halts with m zeros on the tape, then we say that the function that it's computing on that input, f of I1 through ik, is m. So 0 to the m is an encoding of the non-negative integer m. All right? So if the Turing machine, you give it a bunch or a tuple of non-negative integers using the unary encoding and separating the elements by 1s, and it halts leaving m zeros on the tape, then whatever function it computes, it is such that f of the input is m. Okay? Fair enough? Okay, if a function f of k inputs is computed by some Turing machine, we say that this function is a partial recursive function. So any function that can be computed by a Turing machine in the sense that we just described, meaning if you give the Turing machine a certain input and it leaves on the tape the value of f on that input, then it's computing this input. Then this function f is called a partial recursive function. It's computable, all right? Further, if this function is defined for all possible inputs, then we say that it's a total recursive function. Now, some functions are not defined for all possible inputs, so you may imagine that you take the function 1 over x, for example, and it's defined for all integers x except 0. So it's undefined for 0. And in that case, we may say that it's not a total function, it's a partial function, because it's not defined for some possible inputs. Now, if f is undefined for some possible tuples, then it's not a total recursive function. But if it is defined for all possible tuples, then we say it's a total recursive function. And imagine that if f is defined for all tuples and it's partially recursive, which means it's computed by some Turing machine, then this Turing machine, given any input tuple, will have to leave the value of f on the tape, which means that it will have to halt. So Turing machines that are computers of total recursive functions never run forever, because whatever input you give them, they have to give you an output. Okay? Now, in that sense, partial recursive functions are analogous to RE languages, recursively enumerable languages, or Turing recognizable languages. Why is that? Because they are recognized, or they are computed, I'm sorry, by Turing machines that may run forever on some inputs, basically those input tuples for which f is undefined. But a total recursive function, which is defined for all possible input tuples, are analogous to recursive languages or Turing decidable languages, because the Turing machines that compute them never run forever, because they will always have to stop and give you the answer f of the input on the tape. Example. We want to define what is called proper subtraction of n from m. So the proper subtraction of n from m, where both n and m are non-negative integers, will be basically m minus n, the subtraction of n from m, when m is greater than or equal to n. Basically, when the result will be non-negative, right? And it will be 0 otherwise. So for example, the proper subtraction of 3 from 5 is 2. But the proper subtraction of 3 from 2 is 0, right? Because 2 is not greater than or equal to 3. So we want to construct a Turing machine that will compute proper subtraction. Now here is an example of how this machine will work. So suppose you give it as input. Suppose this is the input to the machine. Now what does that mean? Remember, this machine will take two numbers, all right? N and M. Excuse me, M and N, all right? So this is M and this is N. So M is 3, and then there is 1, and N is 2. Okay, so what do we do? Basically, you erase. You replace it with a blank, that is. You erase a leading 0, the first 0. Okay? That's what you do here. Then you go all the way until you find a 1, and then you look for the next 0, which is this one. You replace it with a 1. Good. Then you go back, right? All the way to the left until you find the blank. Then look to its right, that's a 0, erase it, replace it with a blank. Then go all the way to the right until you find a 1. Now look for the first 0 after the 1s. Now this will be the 0, replace it with a 1. Move to the left until you find the blank. Go to the right. Is this a 0? Yes, it is. Then erase it, replace it with a blank. Then go to the right until you find the 1. Yeah, that's a 1. Then keep on moving until you find the 0. Yeah, we reached the end without a 0. Then that means that you're done with n. All right, you removed all the zeros in n. But then, remember, now you have nothing in m as well, right? You have erased everything. Why did you erase everything? Because you removed this 0, right, in the hope to find a matching 0 on the other side to kind of remove it as well. So if this happens, you go back to the blank, right, and then go to the right and replace this one with a 0. Then basically remove all the remaining ones by replacing them with blanks. You end up with a single 0. Now, isn't this the correct result? Isn't this 3 minus 2? Yeah, sure, that's 1. That's the unary representation of 1. And how did we do it? You remove a 1 from here, a 0 from here, and a 0 from here, right? A 0 from here and a 0 from here, a 0 and a 0. But you prematurely remove this 0 before checking that there is a matching 0 here, and this is why we had to restore that. Here's another example. This time it's 2 and 3. So m is 2 and n is 3. So now the result should be 0, okay? Because now m is not greater than or equal to n. So you do the same thing again. You replace this 0 with a blank, move to the right until you find the 1, go to the next 0, replace it with a 1. Then move to the left until you find the blank, right, that's a 0, replace it with a blank. Move to the right, you find the 1 immediately, keep on moving until you find the 0, replace it with a 1. Go back, until you find the blank, the blank, then move to the right, but this is not a 0. So you're done with all the zeros that represent M. So what you need to do, whether there are remaining zeros or not, that means that you were done with M before N. So the result should be 0 in that case. So basically you replace any symbol on the tape with a blank and you leave the empty string, which is the unary representation of 0. So we're going to define proper subtraction of N. That we said already. Okay, so here is the answer. It's kind of a description of what we just said. The input is in general of the form 0 to the m, 1, 0 to the n. Here is the main loop. We're going to replace a leading 0, meaning a leftmost 0, by a blank. Search right for the first 0 that follows a 1. Replace that 0 by a 1, just exactly as we did in the examples. Move to the left end of the tape and go to step 1, right? Find the leftmost 0 and replace it with a blank. Keep on doing this forever. Not forever, of course. Now this loop ends if either in step 1 there is no leading 0, which means that you're done with M, okay? And in that case, replace any symbol on the tape by a blank. This will happen if M is less than or equal to N. So this is one way to end. Or if in step 2, when you're searching right for the first 0 following a 1, and this happens when you replace a leading 0, a 0 from M that is, by a blank. You encounter a blank after the ones, which means that you were already done with all the zeros in N. Now, in that case, like we saw in the first example, you replace the first one by a 0. So you go back until you find the first one, replace it by a 0, and replace the rest of the ones by blanks. Okay? A second example. Construct a Turing machine to compute the product of two non-negative integers, m and n. So we want to basically do multiplication now. So here's the idea. We're going to use a 3-tape Turing machine. We're allowed to use multi-tape Turing machines now. And the input, 0 to the m, 1, 0 to the n, is initially on the first tape. So for example, if m is 2 and n is 3, this would be the input. Right, 2 zeros, the unary representation of 2, then the separator, the comma, 3 zeros, the unary representation of 3. All right. Pre-processing step. We're going to mark the left ends of the 3 tapes by the dollar signs. Okay, so write a dollar sign at the very end. We saw how to do that in the last lecture. Then copy the m zeros onto tape 2. Right, so the m zeros are copied onto tape 2. The copy starts, of course, on the second square after the dollar sign. Copy the n zeros on tape 3. So the n zeros are copied onto tape 3. Replace any symbol on tape 1 other than, of course, the dollar sign by blank. So basically clear everything here. Move the 3 heads to the second square from the left. So second square from the left, second square from the left, second square from the left. Now we're ready to go. Cross a 0 off tape 2. Right, so we're going to cross a 0 off tape 2, replace it with an X, and move, of course, to the right. Move head 2 one step to the right. Make a copy of the zeros off tape 3 onto tape 1. So we're going to copy those zeros onto tape 1. How are you going to do that? Well, basically, look at what that head is reading and write it here. Move to the right. See what it's reading and write it here, and so on. So you make a copy of those zeros down here. Okay? Move head 1 to the first blank. This should follow a string of zeros, of course, right? Yeah, unless n is 0. So there is nothing here, unless there is nothing in that case. Then move head 3 back to the first 0. So we're back here. So when you're done with this loop, this will be what you have on the 3 tapes. This is what's on tape 1, a copy of n, right? A single copy of n, and then the head is here. That's what's on tape 2. You're already done with one of the zeros in the representation of m, and the head is at the second one. And tape 3 is as is, and the head is again in that position. Right? Then you keep on doing this. Now the loop ends if in step 1 no zeros are left on tape 2. and the output is now on tape 1, starting at the second square from the left. Now if you do this again, right, let's start to do it again. So you're going to replace that 0 with an x, okay? Then you're going to make a copy of those right here. So you're going to copy 3 more zeros here. You have 6 zeros, okay? Then when you loop and try to do this again to cross a 0 off tape 2, you will find that there are no more zeros. You're pointing at a blank now, and then you're done, and that's the answer. That's actually 2 times 3. Why is that the answer? Because you basically made m copies of n, right? So you, as if you're adding n to itself m times, which is exactly what m times n is. So I guess I will stop here because we're kind of running out of time, and I will not be able to start talking about enumerators, and we will kind of postpone our discussion of enumerators to the next lecture. Thank you so much.